Today we're going to talk about interference of electromagnetic radiation, and I will start as a warm-up with the famous historical experiment which was first done by Young in 1801. By that time, the issue whether or not light was waves or whether it was particles was still unresolved. Newton always wanted light to be particles, but the Dutch physicist Huygens wanted them to be waves, and the issue was unresolved. Let us agree that if light are particles, and you have a screen that, say, has two openings, and you would throw particles through there, like tomatoes are particles, and you collect them here, then those tomatoes that don't get stuck on the screen, but that make it, would form a pile here of tomatoes, and they would form a pile there of tomatoes. That's very typical for particles. But the situation is different when we deal with waves, because the moment that you have waves coming in, say, for instance, we have plane waves coming in like this, then the wave can go through both openings simultaneously, and that changes the picture quite dramatically. It was known, of course, already in the 17th century that if you have water waves going through a small opening, so here are water waves moving in like so, and here is also water, that what you see coming out there are circular waves. The waves then look like this, and they're propagating out in a circular fashion. And if the velocity of the waves here is the same as the velocity there, then the wavelength here would be the same as the wavelength there. But if the velocities are different, of course, you will see a change, a difference in the wavelength. So Huygens, my countryman, suggested in the 17th century the idea, which is now known as Huygens Principle, that we can think of this in a very different way. Huygens, by the way, is difficult to pronounce. Anyone of you who knows how to say Huygens correctly is also Dutch, because you miss the ui in your language and you miss the ch in your language. And the combination of ui and ch is a complete killer for you guys. You know, you don't get extra 803 course credit if you can come to my office and say Huygens, but it will certainly put you in the Dutch category. So in the 17th century, then Huygens came with an idea which was later amended by Fresnel in the 19th century, and it is now known as the Huygens, I will pronounce it your way, the Huygens Fresnel principle, which works as follows. If we have a plain monochromatic wave, and it's incident on a screen with an aperture, so this would be an aperture, an opening. Here you would have two apertures, two openings. Then the Huygens Fresnel principle states the following. All points in the aperture plane may be thought of as secondary point sources of spherical waves. And the point sources replace the real source which is flooding the screen, and the screen itself is a perfect absorber of the radiation falling upon it. And so I will repeat the Huygens Fresnel principle, which I will need today. All points in the aperture plane may be thought of as secondary point sources of spherical waves. In the case that we had water, this is a two-dimensional surface, they would be circles. But when you deal with light, you can think of them as three-dimensional, that means spherical waves. Now the Huygens Fresnel principle is very powerful, though there is a wide range of opinion to its scientific merit. And in a very famous book, The Principle of Electrodynamics by Melvin Schwartz, I read the following, and I quote verbatim from his book. He says, Huygens' principle tells us to consider each point on a wavefront as a new source of radiation and add the radiation from all the new sources together. Physically, this makes no sense at all. Light does not emit light. Only accelerating charges emit light. Thus, we will begin by throwing out Huygens' principle completely. Later we will see that it actually does give the right answer for the wrong reasons. So I will proceed my lecture today to get the right answer, but perhaps for the wrong reason. Suppose now we have a electromagnetic wave. I'm particularly thinking of light. And I have here an opening, and I have here an opening, and plane waves are coming in from the left, moving with the speed of light. And let this opening be A, and let this opening be B. And here the center of the two is O. This could be a circular opening, it could also be a slit. Most of the experiments I will do today are with slits, which are perpendicular to the blackboard. So they are very narrow openings. Imagine now here a point P. And so the wave from point A will reach that point P, but the wave from source B will also reach that point P. And so the electric vectors there are going to be added, of course, vectorially. Imagine now that BP minus AP, imagine that were 1/2 wavelengths. Then what you get is that the mountain of the E vector here will coincide with the valley of the E vector from the other one, and so you will get the situation that light plus light will give darkness. We call that destructive interference. The wave from here and the wave from there would be 180 degrees out of phase. And if you take all the points for which the difference is 1/2 lambda, that is a hyperboloidal surface. It's like a bowl. It's not only in the blackboard, but it also comes out of the blackboard. It's like a bowl. Remember from your high school days that if the sum of the distance AP and BP is a constant, then you get an ellipse. But if the difference is a constant, you get a hyperbola. So you will get a hyperboloidal surface, and everywhere on that surface, BP minus AP would then be 1/2 lambda. And then you would get the amazing consequence that light plus light would give darkness, destructive interference. Tomatoes don't do that. One tomato on top of another tomato does not give no tomato. That is distinctly different from particles. Now, of course, there are also hyperboloidal surfaces for which there is constructive interference. In other words, if I make this difference n times lambda, whereby n is either 0 or plus or minus 1 or plus or minus 2, then I would get surfaces for which we get construct interference. Then the phase difference between the two waves is either 0 or 2 pi or 4 pi. So we have surfaces with constructive interference, and then we have surfaces with destructive interference, and that's going to be at the heart of what I want to discuss with you now. So I will start a new drawing. I think we don't need this anymore. And I will now have a screen with two narrow openings. They could be slits, as I said before. So here is one opening, and here is the other opening, and let the separation between them be D. And the upper one you can call source number 1, and the other one source number 2. Suppose now that we are looking at this at a distance which is very far away. Very, very far away. And where you are located in space, seen from this point, is an angle theta. So the wave from this source will reach you. And since that point is very far away, these lines here are, of course, parallel to each other. Very close to parallel, because it's very far away. The wave that comes from this one has to travel over a larger distance than the wave that comes from this one. And that difference can easily be expressed algebraically. If this angle is 90 degrees, that difference is this much. That is how much further this wave has to travel than this one, and then they vectorially add very far away at the location where you happen to be. And this difference here is d sine theta. That's immediately obvious. If this angle is theta, this angle is also theta. So the path difference is d sine theta. And that translates into a phase angle difference between the E vectors. Theta. First of all, d sine theta, which is the path difference, this is how many wavelengths you can fit on that path difference. So I divide it by lambda. And for each wavelength that I can fit on there, the phase difference is going to be 2 pi. And so the phase angle, the difference between the wave from here and there, is therefore 2 pi times d divided by lambda times sine theta. And so now I can set the condition for constructive interference. So constructive interference. What I want is, I want delta to be a multiple times 2 pi. So again, I already wrote that down earlier, but I will do that again. N can be 0, it can be plus or minus 1, it can be plus or minus 2, etc. If n is 0, by the way, you are right at this plane, which comes perpendicular out of the blackboard. Clearly, when you're on this plane, when n is 0, the distance to any point on the plane from source number 1 and source number 2 is obviously the same. You can also write down that d sine theta, and I'll give it a little n, which makes connection with this n, it's nothing to do with index of refraction, that d sine theta is now a multiple times 1 wavelength. That's saying the same thing. So this statement here is the same as this statement. There's no difference between them. And now we can write down the condition for destructive interference. So now you want that delta is pi, 3 pi, 5 pi. So now you have delta equals 2n minus 1 times pi. And if you want to write it down in terms of the d sine theta, then you get that d sine theta of n, which is that n that you see there, is now 2n minus 1 divided by 2 times lambda. And so this is at the heart of the idea of the interference, in this case, of 2 of these sources, 2 slits or 2 circular openings. Let me check that we have that right. D sine theta, the n makes connection with the n, equals n lambda. Delta is a multiple of 2 pi. Destructive interference, we get 2n minus 1 times pi. Yes, I can live with that. Now I want to be quantitative, because I'm going to do a demonstration very much with the numbers that you're going to see now on this blackboard. I'll give this back to you, although you may not need this. So we now have the 2 openings all the way on the left here, and they are so close together, so this is that screen, they're so close together that you can't even separate them anymore. So this is the point where the 2 openings are. And we are going to look on the screen, which is far away. So here is a screen, which is going to be that screen, and we want to see how the constructive interference, that means light, shows up on the screen, and how the destructive interference, that means darkness, shows up on that screen. And so here are these 2 openings. So light comes in from the left. And let this distance be L. And so I want to know, if I look under an angle theta, as seen from the slits, I want to know what kind of pattern I will see. Let's call this x equals 0. And we call this x, positive x, and that's negative x. You can also say that the sine of theta, if you want that, is approximately x divided by L, but that's only true for small angles of theta. And with this kind of interference, we sometimes have angles of theta which are not small at all. So I want to warn you that this is not something you can use universally, but today you will see that we can use it. So I start now with red light, lambda, is 600 nanometers. So that's the light I will use. So I use monochromatic light. And we will have a distance to the screen which is about 5 meters. The setup is here. This is about 5 meters. And we have light from a red laser, which is a little larger than 600 nanometers, but I just want some round numbers. And the separation here, d, between the two slits is 1/4 of a millimeter. Now, you may think that that is rather small. Well, you will see that that's what you need. You need very small values of d to even see this phenomenon. So now, let's evaluate what n is. Let's evaluate what delta is. Let's evaluate what the sign is of theta of n. And then we will evaluate what x of n is. And we will do that for constructive interference. So the numbers that you're going to see here is for constructive. And of course, if you want to, you can do the same exercise for destructive interference. I need constructive interference, so I have to turn to delta is that, and I make them n times 2 pi. And I start with n equals 0. Well, that's easy. N is 0. Delta is 0, the sine theta n is 0, and x of n is 0. That's where you will see maximum light, constructive interference. Obviously, that's the plane that goes right through the middle of those two openings, and the distance to each one of those sources everywhere on that plane is, of course, the same. And so you expect here to see light maximum. Now I go to plus or minus 1, and I calculate now what delta is. Then I get plus or minus 2 pi. And so the sign is now 2.4 times 10 to the minus 3. You can check that, because you know what the d sine theta is n times lambda. And I told you what lambda is. D sine theta is now n times lambda. And we take n equals 1, and you know what lambda is. You know what d is, so we can calculate the angle sine theta. And that translates then into an x value of about plus n minus 1.2 centimeters. So now I know what the sine of theta is, and I use the small angle approximation, which is more than adequate. And I know now where on this screen I get, again, maxima. And that is then here, 1.2 centimeters on this side, and 1.2 centimeters on the other side, because you get, of course, plus as well as minus. And then I can continue for n equals 1, n equals 2. I will just do plus or minus 10. So then you get here plus or minus 20 pi. So then you get here 24 times 10 to the minus 3. And so you get plus or minus 12 centimeters. It's almost linear, because the sine of theta for these small angles is still the same as theta in radians. Now, before I show the demonstration, I want a little bit more information on the shape of the dark and light areas that I'm going to see. So what I plot here now is, I will lower this and I will raise it later, because I want to work above my head so that you can see what I'm doing. So I'm plotting here the sine of theta. And keep in mind that is linearly proportional with x. But I always prefer to plot the sine of theta. And so here is 0. Let here be lambda divided by d. That is where my first maximum will come. You can see that. And then here, the same distance, I have 2 lambda divided by d. And on the other side, I have minus lambda divided by d. And all of these are maxima, constructive interference. And the destructive interference clearly falls smack in the middle. I did not calculate them. And so the destructive interferences are here. And so you get light curves, light intensity, which is like this. Light intensity, remember, is always the pointing vector. So this is light intensity. And that is in watts per square meter. Now the first thing that I want you to notice, and you will see that today in various demonstrations, is that the location of the maxima depends on the wavelength. So that means if red light, 650 nanometers, if that falls here as a maximum, and it falls here as a maximum, and it has here a maximum, and it has there a maximum, that blue light, which would have a wavelength, say, I pick 400 nanometers, would not have its maximum at the same location, therefore not the minima either. Because look at the relationship. N d sine theta is n times lambda. And so the angles of theta are different. And so you would get here roughly, it's about 2/3 down the way. Yeah, you will get here roughly the maximum for blue. You would get here the maximum for blue. Notice that for n equals 0, the red and the blue have the maximum at the same location. But you would get the first maximum, the blue here. You would get the second maximum here. And you would get the third maximum almost exactly at the location where you get the second maximum for red. The reason being that 2 times 650 is very close to 3 times 400. That's the reason. So each lives a life of its own. The light intensity that you see is a cosine square function of delta divided by 2. And this is so fundamental that first I thought I will ask you to derive it, but then I decided to spend 1 minute on it and derive it for you, because it's extremely important that we use that later in our predictions. So let us assume that source number 1, and the other one I call source number 2, for that source number 1, E01 has an E1, sorry, not E01, but E1, has an amplitude E01 when it reaches the screen, and then, of course, you have cosine omega t, and this is the frequency of the light. That's the electromagnetic radiation. E2, that is the other source, has E02 times cosine omega t, and here is that crucial delta, which is the difference between the two in phase. That's why you get maxima, and that's why you get minima. That's the whole idea of the interference pattern. Now, if you're very far away from the two openings, then these E vectors are, of course, very closely the same. Remember, E is proportional to 1 over r, but if the distance r is very closely the same, then we can assume, to good approximation, that the E vector, the amplitudes are the same. So that means the total E vector that you get, the sum of the two, vectorial sum of the two, is then going to be 2E0. I simply call it E0 now. And then I get the cosine of half the sum. So I get the cosine of omega t minus delta divided by 2 times the cosine of half the difference. So that becomes the cosine of delta divided by 2. And now you see why the light intensity is proportional to cosine square delta over 2. Because when you calculate the mean value of the pointing vector, you have to take E cross B. And so B also has this term, and also has this term. And so you get the square of this term, and the square of this term. But the average of the square of this term is 1/2, so forget that for now. And so you see it is going to be proportional to the square of delta over 2. And so this function that you see, delta is linearly proportional to sine theta. This curve that you see is a cosine square curve. The experiment that I'm going to show you has a separation of the slits, which is 1/4 millimeter. My wavelength is 650 33 nanometers, which is very much the same, and the distance to the screen is about 5 meters. And so the way that we have this arranged is that the two slits, they are vertical, they are like this, and so this separation is 1.4 millimeter, and then we put over there a laser beam, and then the result is what you're going to see there. And so I now have to think about, this is where it is. You're going to see it there, and in order for you to see it, I have to make it completely dark. When you look here on the screen, you will see areas which are distinctly dark, and you see areas whereby you see the light. In other words, you see the pattern that we just calculated. You see constructive interference and you see destructive interference. And you're looking here at an experiment that is historically of great importance. It is one of the most mysterious and puzzling issues in all of physics. This interference pattern, which was first shown by Young in 1801, is clearly convincing evidence that light is a wave phenomenon. However, 20th century physics has shown that light comes in the form of individual photons with well-defined energies, and photons can behave like bullets. They have momentum, they produce radiation pressure, and they can be localized in space. We can detect individual photons in a way that we detect individual tomatoes. Photons behave like particles. However, the interference pattern that you are staring at on that screen can only be explained if we assume that each photon went through both slits. But how on earth can one particle go through both slits? It will have to be one slit or the other. And here lies the great mystery. Light is both. It is a wave if you want it to be a wave, and it is a particle if you want it to be a particle. If you manage to determine for every photon through which of the two slits it went, and that is possible, if you do it at very low light intensity, you can really determine through which of the two slits each photon went, then you will not see any interference anymore. The pattern on the screen will be like that of the tomatoes. You get two piles. So the moment that you establish the particle character of the light, by determining through which slit it went, you have destroyed its wave character. And it will not behave like a wave, it will behave like a particle. However, as long as you do not determine through which slit the photon went, thus as long as it remains your guess through which one it went, light will reveal to you its wave character, and you will see interference. The choice is yours, but you cannot have it both ways. And so you're looking now at something that had a huge impact on physics. Clearly, at the time that this experiment was done, it was accepted that light are waves, but we now look at it in a very different way. I want to show you a slide of this, what we call double slit interference, in white light. We did it in red light. That's the easiest, and you get very sharply defined maxima and minima. And the reason why you get them so sharply defined is because you don't have the interference of the other color. But of course, if you do it with white light, then you will see the blue light has its own spacing and the red light has its own spacing. And the net result, of course, is that you see a somewhat different pattern. And that I will show you here. I will make it a little darker for that. So the upper panel is then the double slit interference in blue light. And you see the clearly dark lines, which are the destructive interference locations. And you see, as I already indicated on the blackboard, that the separation of the red is larger, because it's wavelength dependent. And if you then do it with white light, then you see something like this. So it's more difficult to actually see the maxima and the minima. Now what you can do with light, if you can turn light plus light into darkness, then obviously you should also be able to turn sound plus sound into silence. It's just a matter of scaling up the whole experiment. And that is what we have set up for you here. We have two loudspeakers. And so all the equations that you have here apply verbatim, except that we scale it a little bit. So our D is no longer a 1/4 millimeter, but our D is now 1.5 meters. So here is a source of sound, and here is a source of sound. And they are fed by the same electronics. And so the D, the separation, is 1.5 meters, and the frequency is 3,000 hertz. So we do this experiment now for sound. And so lambda is about 11.3 centimeters if you take 340 meters per second for the speed of sound. So we have, in a way, monochromatic light, monochromatic sounds, more or less one wavelength. And so you can calculate what lambda divided by D is. It's about 0.075. And so you can calculate where now those surfaces are. They are really hyperboloidal surfaces. They're coming out from the center here, and they bend in your direction, where all those hyperboloidal surfaces are, where there is no sound. And then you can calculate where all those hyperboloidal surfaces are, where there is sound. Let's first calculate how many hyperboloidal surfaces there are. So in order to do that, we simply have to stick in our equation, d sine theta equals n lambda. We just put in theta is the maximum value possible, and that is 90 degrees. So you put in theta max, and that is 90 degrees, pi over 2 radians. And so when you do that, you'll find that n max, that is the highest number of n in that series 0, 1, 2, 3, 4, 5, that n max is then d divided by lambda, which in our case is about 13. It is 1 over this number. So that means there are 13 of those surfaces going in this direction, but there are also 13 going in this direction. Remember, you have plus and minus. So you really have to multiply this by 2. And so there are 26 surfaces, no more and probably no less, in this audience of constructive interference. And then there are probably also around 26 destructive interference. So now I want to be as quantitative as I can be, and I would like to know the students who are sitting about 5 meters away from me, what the distance is between one maximum, the 0-order maximum, right at the center, and the next maximum. We get an idea where to search for those maxima and where for those minima. So I will go now for the maxima. So I know that at theta 0, right here, all of you here sitting here must hear a maximum there in this plane. Now the question is, where is the next maximum? Well, the next maxima depends, of course, on the distance, how far you are sitting away from me. So I take the students which are about 5 meters away from me. The sign of theta 1, this 1 now makes reference to n equals 1, that is the first surface away from the center. So the sign of theta 1 is then 0.075. And that translates into a value of theta 1, I think it's about 4.3 degrees, that's right. And so now you can calculate what the separation is between one maximum and the next maximum. That separation x1, I call it x1, is roughly L times that 0.075. And that is about 38 centimeters. So right there, those guys that I'm looking at now, you will have a maximum sound here, and when you move 38 centimeters, you will have another maximum, and there is a minimum in between. So the minima and the maxima right there, where Eliseo is sitting, is about 19 centimeters. Now for you there in the back, it is larger. And for you here in front, it is smaller. Because remember, those surfaces go like this, and so here the separation is smaller. I just give you this as an example, that you know roughly an order of magnitude of what you are looking for. So I'm going to turn on this sound now, and then I want you to wiggle back and forth, as you did when you were in nursery school, and I want you to find the locations of maxima and minima. And I can assure you that the ones with minima, the ones with sound silence, are extremely well defined, because of course we have done this several times ourselves. Don't move too fast, move very slowly, and there will be points where you hear no sound, and there will be points where you hear a lot of sound. So are you ready for this? Keep moving. Most of you move too fast. Who was able to clearly distinguish the maxima from the minima? Not too many, eh? And the reason is that all of you are lousy scientists. If the difference in space between maxima and minima is 19 centimeters, that is this much. What is the separation between your two ears? It's about 20 centimeters. It's not an accident that I chose that. So if you have a maximum here, you would have a minimum there. So what do you have to do? You have to close one ear. And then you will be real scientists. So I'm going to turn it back on again. I want you to close one ear, and then you will be able to find those minima and those maxima. Move again back and forth. Now there may be some reflections from the wall which may interfere with this experiment. No pun implied. Go slowly, go very slowly. It's remarkable. Unbelievable. I hear nothing here. I hear a lot of noise. So who heard it now? Ah, there you go. All right, this is the great moment for the mini break. This is a mini quiz. So if someone is going to help me. I owe you something regarding exam 2. Here you see a histogram of exam 2. And what is interesting, and in a way helpful to me, is almost bimodal. Now we have 47% to go in the course, of which 40% is for the final alone. And so clearly I can't say much about dividing lines between A, B, C, D's, and F's. I want to make only a global statement. And I only warn those of you who I put in the danger zone. The danger zone for me are students whose cumulative, assuming that they've taken all the exams then, whose cumulative is less than 30 or near 30. And those are really the students almost exclusively who have less than 45 for exam 2, or approximately 45. So this is the danger zone. Now that doesn't mean that you will fail the course. It's just a matter of probability. I would say it's high. And then those of you who are dying to know whether they're going to get an A, all I can say is that if your cumulative now is more than 45, assuming that you've taken all exams, then you will probably end up with an A. Will you end up with an A? I do not know. It's all a matter of probability, but the chances are you may. So that's as far as I can go regarding the dividing lines of course grades. So now I will continue the idea of interference, which has very far-reaching consequences, and I will turn to what we call thin film interference. And I will cover normal incidence. It really doesn't change very much if you change to a different angle. The concept is the same. Thin film. I have here a thin film of oil, and we will shortly see what I mean by thin. So this is air, so we have plane waves of light coming in this way, so it's normal incidence. And this is N1, which is air, so that's about 1. And this is N2, which for oil is about 1.45. Let's make it 1.5, just so we round it off. And this is N3, which is again air in this case, so let's make it 1. It doesn't have to be air, but I will make it air. And let the separation, or the thickness, I should say, of the oil be D. And I call this surface A, and this surface between oil and air, I'll call that B. So let light come in, normal incidence, comes in from above, over a large surface. I'll just put in one arrow here, and let that intensity be I0. And now I'm going to calculate how much is refracted back into the air. And I put the arrow here, so I offset it, just for the purpose of clarity. So some of it is refracted, and some of it goes straight through. And all of you are more than capable of calculating how much is refracted. At that point A, the R, the reflectivity of the E vector, is N1 minus N2 divided by N1 plus N2, and that is minus 0.2. The minus sign tells you that there is a flip here in the E vector by 180 degrees. The intensity of the light that is reflected is then 4%, the square of this number. And if 4% is reflected, then clearly 96% goes through. So if this is 100, then this is 4.0, and then this is 96. So this light here hits the surface at B, the boundary between oil and air, and some of that light goes through, which I'm not interested in, and some of it comes back. And so I can calculate, again, the R value for that surface near B, which is now N2 minus N3 divided by N2 plus N3. N2, this is N3, and so that is plus 0.2. So there is no flip in the E vector as it returns. And the fraction of the light that is refracted is again 4%. However, it is 4% of the 96%, because only 96% go through. And 4% of 96% is 3.84. When it reaches this surface here, again 4% will be reflected, and 96% will go through. So what comes out here then ultimately is 96% of this number, which is 3.7. I now want to ask the question, what happens when you are looking here from above and you see this light coming back straight from A and this light coming back at you, which made this journey through the oil, whether or not the combination of those two can constructively interfere and whether they can destructively interfere. Now, as far as destructive interference is concerned, let me make a qualitative statement. The intensity of this is 4, and the intensity of this is 3.7. So it can never be completely darkness, but you can never kill 3.7 intensity with 4. But if they're 180 degrees out of phase, which we will be able to do, there is very little light left. There will only be the difference, which is 0.3 left. So it will be quite dark. But I will still call that constructive and destructive interference. So the question now is, what is the phase difference between this light here and this light there? Phase difference. That's what matters. Well, let's first look at the difference in path. The difference in path is clearly 2D. Because this light has to go in this direction, that is D, and it has to come back, so that's 2D. So now is the question, how many wavelengths fit on that separation, on that distance 2d? Wavelengths in oil, of course. That's what matters. So that is this many. So what now is the phase difference? Now we have to multiply this by 2 pi. Because if this were 3, then the phase difference is 3 times 2 pi. For each wavelength, you get a phase difference 2 pi. So now you have to multiply this by 2 pi. So now you may think, and that would not be unreasonable, that this is the phase difference between this radiation and this radiation. But what have you overlooked when you do that? That's right. You have overlooked the fact that there is here a flip of 180 degrees, which does not occur here. So there is an additional pi in the phase difference. So I'm going to write down here now the total delta. So delta is now 4 pi times d. Now I can write this as lambda oil. It's perfectly fine. I can do that. I prefer to write it as lambda air, and then all I have to do, of course, is divide the lambda air by the index of refraction of oil. And so, yes, I could have written lambda oil here, but I prefer to write here lambda air, and then all I have to do is multiply this by N2. Yeah, that is that 1.5. It's the same thing. And so this is then the delta that we calculated from here, and then we have to add pi. And the pi then is the consequence of this minus sign here, which you don't see here. Keep in mind, if someone wants to be nasty to you during an exam, of course not I, but if someone wanted to be nasty to you on an exam, they could make N3 larger than N2. What would change in this equation? The pi would disappear, that's all. The rest would remain the same. So don't think of this as a universal equation. There's no such thing. So this pi is the result of the fact that here N2 is larger than N1, but that here N3 is smaller than N2. That's why you get only pi. So now we are in business. We now have here the criterion for constructive interference. You want me to have it higher? What is your...
Your D looks like a delta.
Oh yeah, thank you very much. How could I? It is D, right? Yeah. Uh-oh. Uh-oh. My Greek heritage somehow. No. All right. So we agree, right, that this is in this case, this is the phase angle. So now we're going to ask ourselves the question, what thickness are required to get minima and to get maxima? The first very interesting case is that if you make D equals 0, that you kill this whole term and you only have pi, so that's destructive interference. So there's no question, destructive. Now you may say, yeah, zero film, you know, what kind of nonsense is that? Is that meaningful? Yes, it is very meaningful. I will demonstrate it to you. I cannot make an oil film 0 thickness, but that's not necessary. All that is necessary that this D over lambda oil becomes exceedingly small, for instance 1/100th. So if I make D 1/100th of the wavelengths of light in oil, then I'm close enough, and you will indeed see then, I will do this with soap, that in reflection you will see no light. You get completely destructive interference. Apart from the fact which I mentioned, that there is an imbalance between the 4.0 and the 3.7. That's a different issue. So we will even be able to enjoy the D equals 0. But now I want to be more general. I want to give you a feeling quantitatively for what you're going to look at. and also a feeling for what thicknesses are really necessary to see these colors. And so I am going to address now only the case of destructive interference. And I'm going to choose a lambda in air of 400 nanometers. That's my choice. So that means that my lambda in oil is 400 divided by 1.5, which is about 267 nanometers. And now I want to calculate for what thicknesses d I'm going to get destructive interference. So I'm going to set this equal to 2n minus 1 times pi. That's all I do. And I choose n equals 1. And what do I find? I find d equals 0, of course. We knew that already. We just discussed that. Because if n equals 1, then that requires that delta is pi. And if delta is pi, then this term is 0. So you see that d is 0. You can immediately see that. So now we take n equals 2. And if you substitute for n equals 2 in this equation, you get 3 pi. And this is already pi, so this has to be 2 pi. And so if now you calculate what d is, you find that d is 133 nanometers. Well, that's obvious. It obviously must be half of the wavelength of the light in oil. Because if the wavelength of light in oil is 267, you have to travel this distance twice. And if you travel this distance twice, that is exactly one wavelength. And one wavelength corresponds to a phase angle of 2 pi. And so here you get 2 pi, and it's this pi that kills you, that gives you the darkness. And then n equals 3, you'll find that d is approximately 267 nanometers. So now 2d translates into 2 wavelengths. Now I'm going to choose this thickness. And with that thickness now, I'm going to work, and I'm going to radiate white light onto that thickness. So I select that one for which I already know that in blue light, I kill it. Destructive interference. So we now have white light. And we have d is 133 nanometers, so that is non-negotiable. d is 133 nanometers. I'm going to write here lambda air in nanometers. I'm going to write here delta. And I'm going to write here the cosine squared of delta over 2. That is a measure for the light intensity. It's proportional to that. We discussed that, and I showed that. I derived it for you. Okay, 400 nanometers, blue light. Delta is 3 pi. This is 0. We already calculated that. That's the destructive interference if you make it that layer. If you make it 133 nanometers. Now, I need green. Yeah, we have green. So now I'm going to also shine on it green light, 500 nanometers. So I know what D is, so that's non-negotiable. And now my lambda air is now 500 nanometers. And so I can calculate now what delta is. Untouched by human hands, very simple. And I find now 2.6 pi. And if now I take the square root, not the square root, if I take cosine square of delta over 2, I find 0.35. But now I go to red, and I do 650 nanometers, And now I calculate what delta is, and I find 2.2 pi. Now I get 0.90. Now I am very close to a maximum. And so, this is very convincing that if you make your film this thin, that it will look distinctly red. Maybe not perfect red, but it will look distinctly red. The red color dominates, and the blue practically absent at all, apart then from the imbalance that you may have between the 4.0 and the 3.7. A question that I have asked over the years at the final exam for 803 is whether thin film interference is the result of the difference between the index of refraction between the different colors. And the answer is absolutely not. The index of refraction, I have taken the same for all colors, for all practical purposes. That difference does not explain the colors. The color is explained by the difference in path length divided by lambda. That is why you see colors. It has nothing to do with the index of refraction. You can see thin film interference in soap, and I will try to demonstrate that. You can see it in oil spills on the road. I will show you an example. Only thin films give you colors. Thick films do not give you colors. If you go through the exercise, which I want you to do, to make D 0.1 millimeter, which is, by practical standards, still very thin, you will not see any colors. And the reason is that if you go to this equation and you calculate for which colors you will see constructive and destructive interference, there are so many colors in the visible spectrum for which you get constructive interference, so many you will see that your brains will tell you to see white light. There is not one color that dominates. The n values that you will need, by the way, are going to be very high. They're in the range 500 to 700. Huge values of n are necessary in order to get the destructive and the constructive interference. Go through this exercise on your own, and you will see very quickly that so many colors constructively interfere that the film will look white. So the first thing that I want to do, I want to try, it's not so easy, to make you see these colors with soap, which of course all of you must have seen. In fact, if you just take a shower and you soap yourself, then the bubbles themselves in reflection already have these colors. I'll try to make one that is slightly larger in size. We do not always succeed, but let's try that. So the idea is I want you to see colors. Ooh. Well, maybe you did, but that was a little quick. Now, you see colors, did you? That's all I wanted you to see. Did you see them? If you had said no, I would have done it again, but now I won't. You want me to do it once more? It's not easy, though. Now you saw it, right? Yeah, thank you. Okay, so soap bubbles give these colors because they are exceedingly thin. It also gives you a feeling of how thin they have to be. Really, they can't be much thicker than a few times the wavelengths of light. If they become much thicker, you lose the colors for the reason that I just mentioned to you, that there are too many colors that constructively interfere, and then you don't see it anymore. Now I have a demonstration which is very tricky. It works most of the time, but not all the time. We're going to make a soap film on a metal frame. It's going to be done in this box. So we have a metal frame, and we dip it in soap, and so you get a soap film there. And then gravity will make the film thinner at the top and thicker at the bottom. So as you make a cross-section through here, then the film, so this is then the soap. I can make this so thin that it's completely dark in reflection. That is what I promised you, that D is not 0, but D divided by lambda is so small, maybe 1/20th of 1/30th of the wavelength of light, that it will turn completely black. And as this proceeds, in the beginning, the top will show you colors. It goes through these phases of colors, and then it gets thinner and thinner and thinner, and then it turns completely black. I will show it to you upside down. So don't get confused, and that has to do with the way that we project it. So the thinnest part of the film will be low on the screen, and then the part of the screen that is the thickest of the film will be the upper part. As you look at it, appreciate the fact that when we go into the dark phase, if we succeed, that you are talking about the thickness of the film, which is many times smaller than the wavelengths of light, which is typically half a micron. Okay. Let me first get the film up. Oh, actually, let's not get the film up. Let's just get the light up. Let's turn it off. Here, it has to be completely dark. Didn't we agree it has to be completely dark here? So I'm going to dip it in here. Okay, so the bottom is the thinnest. And you see the colors. You see them? And you see that the thickness changes over the film. And that's why there are areas where the red dominates, and then other areas where the red dominates again. And so the bottom gets thinner and thinner and thinner. The white light that you see now here is the result of Markov's trick. In order to avoid that the film bursts, he has to put glycerin in the soap. And what you see here is the reflection of the layer of glycerin which forms on top of the soap. So we'll have to wait a little bit for that glycerin to also go down, and then you will see the pure soap, and that is then the area, and boy, look at it, black. That area that you're looking here now is way thinner than the wavelength of light. And so the reflection is, well, when I say 0, of course, that depends again on the asymmetry that you have that we discussed here on the blackboard between the 4.0 and the 3.7. It's a little different for water than it is for oil. But you see? Black. You can just look at it for a while. It may burst. You also see some very interesting thin film interference in the glycerin itself, which is the oil layer, which is on top of the soap. This is not uncommon. You may remember when you see oil spills on the road that you sometimes see these very nice structures, brownish, reddish, bluish. But here, look at this, look at this. Isn't that incredible? Isn't that fabulous? Boy, the film is holding up, Marcos. We can't complain. Ah, you see these nice oil structures here in the glycerin? The nightmare that we have always is that it pops too fast, and then you have to do it again, again, again. And our experience is if somehow the soap is not right, then in general, no matter how often you try it, it keeps popping. Oh, look how beautiful. Look how incredibly nice the thin film interference in the glycerin, and then here the total darkness, because the thickness of the film, of the soap, is many times smaller than the wavelength of the light in the soap. I never get bored when I look at it. Isn't it gorgeous? Think about the physics that is going on in there. All right. Let's look at some other phenomenon of interference. Try to remember this. This is a gorgeous picture. So there is a whole family of ways that you can see thin film interference. And in your problem set, we give you 2 problems to work on that quantitatively. And there is also this take-home experiment which supports the problems. And I want to concentrate on those too, because they are very nice to demonstrate, because I can demonstrate them to you in monochromatic light. Whenever you have monochromatic light, that means you don't have white light. Of course, the fringes, we call these fringes, the dark and the bright areas, we call them fringes, show up so much better than when you have white light, because then you get the superposition of all the colors, and the maxima and the minima depend on the color. Remember, for one and the same thickness, you may have destructive interference for one color, but you have constructive interference for the other. So if you do it in monochromatic light, you can see this very dramatically. And then one of the classic examples is, and you can do that at home, and you should do that at home, is the 2 microscope slides. So you have a microscope slide, which itself is way too thick to give you thin film interference. Don't even think about the fact that there is glass there. It will do nothing. Way too thick. Probably a tenth of a millimeter. It's ridiculous. And then there's another microscope glass here. And I exaggerate highly this area in between, because they are lying flat on top of each other. But there is an air gap between them. And this is that air gap. And it is this air gap now that acts like a thin film. So you're going to get interference now of light that bounces off this layer and bounces off this layer. And so it is this thickness D now of the air layer that determines the darkness and the brightness, destructive and the constructive interference. And you're being asked in your problem set to calculate where those maxima and minima are. And you can also do that then with the take-home experiment, and I will demonstrate it very shortly. There's another one which is a classic, which I will also demonstrate, and which is also part of your problem set. This is a lens, a glass lens. The curvature is highly exaggerated, and then here is a glass plate. And so here is now an air gap. And now if you shine monochromatic light on this, then, of course, seen from above, there's symmetry about this line, you will see rings of darkness and rings of brightness. And these rings of darkness and brightness will be very far apart here, and they will be very closely together there. And this is part of your homework assignment to show that. And that has to do with the fact that the change here in thickness is very little because of the curvature, and the change here is much faster. This is called the Newton, these are called the Newton rings. And then when you just walk out on the street, preferably on a day when it is not sunny, when it is cloudy, you look on the ground and you see oil spills. And they have phenomenal colors. I'd like to show you one of my own pictures that I took some time ago of an oil spill. Let me first turn it on, and then we'll make it a little darker. I'll make it a little darker so that you can see it better. I photographed countless oil spills, and actually the reason why I've photographed so many is that always I try to reconstruct thickness of the oil on the road, and I was never very successful. For one thing, you can only get a spot like this. You would think that a car loses some oil, so there's one drop of oil that goes. And then it starts to run out. So you would always think that it is thickest here, and then gradually tapers off near the edges. And I've always been wondered, why then here do you see so much white light? You would expect that perhaps it would be much darker. And so many attempts that I have made to convince myself that it's really thicker here than there, many have failed. But there's no question what you are looking at, of course, is a striking example of thin film interference. And not only that, but you know that this film has to be extremely thin, clearly very close to that, in that range of 100 to 200 nanometers. Otherwise, you wouldn't see over the entire area such beautifully equal blue. And here you see this reddish, which is not pure, it never is, very well defined. So clearly it has a spherical symmetry. So there is probably a drop that then spread out. And so now I want to demonstrate then your microscope. So the microscopes we have here, microscope glass, turn on the CD TV there, if everything works. And we do it with near monochromatic light. This light from a mercury lamp, which is largely in the green. So you see very well established maxima and minima. That's the beauty if you do it with monochromatic light. And so these two microscope slides are just on top of each other. But yeah, there is always a little bit of air in between. And so you can sort of make up your own mind that they may be touching each other, really touching where they have practically no air, for reasons that are not so clear, which must be somewhere here. And that's where the separation between the dark lines is the largest. And then somehow here you see these fringes, the areas of darkness and maximum constructive interference. And when I push on one side of these slides, then of course I change this very subtle structure of light in between these microscopes. And then you will see an immediate change in the separation of the lines. So I'm just pushing on it now, changing the configuration. And now this is the point of contact, more or less. And you can really see that. When I'm looking at it right now, I see it just as well as you can see it there. And so you should really do that experiment at home because it's part of your take-home experiment. So I mentioned in the write-up that it's not necessary that you turn in a written summary of your experiment, but so it won't count for your problem set as such, but I will hold you responsible on the final. So I advise you to do the experiments because I may ask a few questions which you can only answer if you actually did this experiment. Here I have two flats, like the microscopes, but thicker. So they're a little sturdier. And this is the way that opticians actually test their optics. So there is here an air gap that grows in size, and when you push, I push now on it, you see now I make them flat. Now I see almost no fringes. Now I push so hard that I open them again like this. So I make one go up like this, and now you see many fringes. Look. You get a huge angle now. And then I want to show you this, which is called the Newton rings. We have it arranged in such a way that with some set screws we can actually push down on this. So we can also make the air gap larger and smaller. And that we're going to show you there. Yeah. I can actually make it even darker. That may be nicer for you. You already see there the center portion of the contact. Where the contact is here, the air gap doesn't change very much. And therefore you will see that the spacing of the rings is large. But when you go further out, then the spacing gets smaller. And it becomes difficult to see, perhaps. But if you're close here, I can really see the rings here much closer than the rings here. And I can put some pressure on there. So in other words, change the geometry a little bit. So now I squeeze a little harder. I hope I don't break it. And when you squeeze harder, they touch each other over a larger surface in the center. You see, therefore it opens up. So over this very large area now is the gap the same. And when I loosen it up, then you expect those rings to become smaller. And this is something I believe that is also part of your take-home experiment. All right, I can't wait to see the result of the mini-quiz. I'll be proud of you if you did well, let me tell you. And I see you then, I hope, on Thursday.